Our universe is a whirlwind of activity. Stars explode, galaxies collide, planets spin. Yet amidst this chaos, some things remain constant. Energy, for instance, can transform, but it can never be created or destroyed. This is a fundamental law of physics known as the conservation of energy. Similarly, momentum, a measure of an object's motion, also remains constant in a closed system. These conservation laws are bedrock principles of classical physics. They govern the motion of planets, the flow of heat, and countless other phenomena. But why do these laws hold true? What underlying principle ensures their unwavering consistency? The answer, as we shall see, lies in a profound connection between symmetry and the laws of nature. A connection discovered by a remarkable mathematician who faced immense challenges and prejudice, yet persevered to revolutionize our understanding of the cosmos, Emmy Noether. Albert Einstein, in his revolutionary theory of general relativity, grappled with a perplexing problem. His equations describing the fabric of space-time warped by gravity seemed to violate the sacrosanct law of energy conservation. How could this be? Was it possible that the very foundation of physics crumbled in the face of gravity? Einstein sought answers, and his search led him to the work of a brilliant mathematician, Emmy Noether. Noether, working at the University of Göttingen, had developed a theorem of profound implications. Her theorem linked for the first time the abstract concept of mathematical symmetry with the concrete laws of physics. Einstein, recognizing the significance of Noether's work, reached out to her. Their collaboration, though brief, proved to be immensely fruitful. Noether's theorem, Einstein soon realized, held the key to resolving the puzzle of energy conservation in general relativity. Emmy Noether's journey to becoming one of the most influential mathematicians of the 20th century was fraught with obstacles. Born in Germany in 1882, she inherited a passion for mathematics from her father, a renowned mathematician himself. Yet, she faced immense discrimination in the academic world solely because she was a woman. Universities in Germany at the time barred women from holding formal academic positions. Undeterred, Noether pursued her passion, attending classes unofficially and conducting research without pay or recognition. Her brilliance, however, could not be ignored. Her groundbreaking work on algebraic invariance caught the attention of renowned mathematicians David Hilbert and Felix Klein, who invited her to join them at the prestigious University of Göttingen. Despite facing continued resistance from some faculty members, Noether finally found a place where her genius could flourish. The University of Göttingen in the early 20th century was a hotbed of intellectual activity. Luminaries like Hilbert and Klein fostered a collaborative and stimulating environment, attracting some of the brightest minds in mathematics and physics. It was in this fertile ground that Noether's genius truly blossomed. Hilbert and Klein recognized that Noether's insights were not only mathematically elegant, but also had profound implications for physics. They encouraged her to apply her talents to solving some of the most pressing problems of the time, including the perplexing issues arising from Einstein's theory of general relativity. Noether, with her characteristic rigor and insight, developed her now famous theorem, forever linking the abstract beauty of mathematics to the concrete laws governing the physical universe. Her work provided a powerful new lens through which to view the cosmos, revealing a deep and fundamental connection between symmetry and the fundamental forces of nature. Section 5. Symmetry's secret: unlocking nature's laws. Noether's theorem, in essence, states that for every continuous symmetry in a physical system, there exists a corresponding conserved quantity. This theorem, formulated by the brilliant mathematician Emmy Noether in 1915, has become a cornerstone in theoretical physics. This might sound abstract, but it is a profound statement with far-reaching consequences. It means that the symmetries we observe in nature are not just aesthetic or coincidental, they are deeply connected to the fundamental laws that govern the universe. Symmetry, in this context, refers to the ability of a system to remain unchanged under a particular transformation. These transformations can be spatial, temporal, or even more abstract. For instance, the laws of physics are the same whether you're in London or Tokyo. This universality is a manifestation of spatial symmetry. This is translational symmetry. Move the entire system in space and the laws remain the same. It's a principle that underpins much of classical mechanics. Noether's theorem tells us that this symmetry implies the conservation of momentum. In other words, the total momentum of a closed system remains constant if the system is not influenced by external forces. Similarly, the laws of physics don't depend on what time of day it is. This is time symmetry. Whether it's morning or night, the fundamental interactions remain unchanged. Noether's theorem connects this symmetry to the conservation of energy. This means that energy cannot be created or destroyed, only transformed from one form to another. This profound link between symmetry and conservation laws provided physicists with a powerful new tool to probe the fundamental workings of the universe. It has opened up new avenues of research and deepened our understanding of the cosmos. Section 6. From spinning tops to cosmic dance, examples of symmetry. Let's consider a spinning top. This simple toy, often found in children's playrooms, is a perfect example of symmetry in motion. The top, despite all its whirling motion, maintains a constant angular momentum as long as no external forces act on it. This fascinating behavior is a direct result of the principles of physics at play. This conservation of angular momentum is a direct consequence of rotational symmetry. The laws of physics are the same whether you rotate the top or the entire universe around it. This principle extends far beyond the spinning top, reaching into the vast expanse of space. The elegance of Noether's theorem lies in its ability to connect seemingly disparate concepts. It bridges the gap between the small and the large, the simple and the complex. The conservation of energy, a cornerstone of physics, is now understood to be a consequence of the timelessness of physical laws. This means that the energy in a closed system remains constant over time. The persistence of momentum is a reflection of the homogeneity of space. This uniformity ensures that the laws of physics apply equally no matter where you are in the universe. These examples, from the everyday to the cosmic, demonstrate the far-reaching implications of Noether's theorem. They show how fundamental symmetries shape the world around us. It provides a unifying framework, revealing that the conservation laws we observe are not mere coincidences, but rather manifestations of a deep underlying order in the universe. This profound insight helps us understand the interconnectedness of all things. Section 7. Noether's theorem's reach, from quantum fields to black holes. Noether's theorem transcends the realm of classical physics, extending its influence to the quantum world and beyond. This profound principle, formulated by Emmy Noether in 1915, has become a cornerstone in the understanding of modern physics. In quantum field theory, the bedrock of modern particle physics, symmetries dictate the interactions between fundamental particles. These symmetries are not just abstract concepts. They have real observable consequences in experiments conducted in particle accelerators around the world. The existence of particles like the Higgs boson, responsible for giving mass to other particles, can be traced back to specific symmetries in the underlying quantum fields. The discovery of the Higgs boson in 2012 was a monumental achievement, confirming theories that had been developed over decades. Furthermore, Noether's theorem plays a crucial role in our understanding of black holes, those enigmatic objects with gravitational pulls so strong that not even light can escape. These cosmic giants challenge our understanding of space and time, pushing the boundaries of theoretical physics. The laws governing black hole mechanics, such as the conservation of black hole entropy, are deeply connected to symmetries inherent in Einstein's theory of general relativity. These symmetries help physicists make sense of the complex behaviors exhibited by black holes. Noether's theorem, even decades after its conception, continues to be an indispensable tool for physicists. It bridges the gap between abstract mathematical concepts and tangible physical phenomena, making it a vital part of ongoing research. It guides the search for new particles and forces, providing a framework for understanding the fundamental building blocks of the universe and the laws that govern their interactions. As we continue to explore the cosmos, Noether's theorem remains a beacon, illuminating the path to new discoveries and deeper insights. Section 8. Exile and Legacy. A star that continues to shine. Sadly, Noether's time at Göttingen was cut short by the rise of the Nazi regime in Germany. As a Jewish woman and a pacifist, she faced persecution and was forced to flee her homeland. She found refuge in the United States, taking up a position at Bryn Mawr College, where she continued her groundbreaking work until her untimely death in 1935. Despite facing immense adversity throughout her life, Noether's contributions to mathematics and physics are immeasurable. Her theorem remains one of the most profound and beautiful results in theoretical physics, underpinning our understanding of the fundamental laws of nature. Her legacy continues to inspire generations of mathematicians and physicists, a testament to the enduring power of her ideas and the indomitable spirit of a true pioneer. Section 9. The enduring brilliance of Emmy Noether. Albert Einstein, in a moving tribute to Emmy Noether, described her as the most significant creative mathematical genius thus far produced since the higher education of women began. This heartfelt praise reflects the profound impact Noether had on the world of physics. Her theorem, connecting symmetry and conservation laws, provided a revolutionary new framework for understanding the universe. It revealed a deep underlying order, demonstrating that the laws governing the cosmos are not arbitrary, but rather manifestations of fundamental symmetries. Emmy Noether's story is one of perseverance, brilliance, and the enduring power of human curiosity. Her work continues to shape our understanding of the universe, a testament to a mind that transcended boundaries and forever changed the landscape of theoretical physics.